Okay, this is lecture 8 or 9. Anybody remembers? Lecture 8 or 9?
8.
Lecture 8, yes. Okay, because we had an exam, so that doesn't count. And today is the 22nd, 2022. All right, so let's see where we are. You remember last time we started introducing you to the concept of rigid body equilibrium, okay? So as I said, if you have any object, right, and this object is obviously supported, is kept in place by some support mechanisms. So you have forces, you have moments acting on this object, both, of course, externally applied, known loads, forces, and also forces that these supports represent, because these supports that are keeping the structure in place also represent some forces, right? So we learned that all of these forces can be replaced by just a single force that is a resultant of all the forces acting on the object. If you move all those forces to a single point, you can replace all of these by their resultant. And then by performing that action of moving all these forces to this point, you end up with also several moments that you need to add to that point. And since this object is not moving, is in equilibrium, these have to be zero. This is the premise of static equilibrium. Or if you recall way back when I started the course, in the first day, I said that static is the study of understanding when you have forces acting on a system, what the response of the system would be. These forces are external forces, regardless of where they come from, that act on the system. And the principle, the governing principle in statics that help us understand and find out what these forces do to the system is that, first of all these forces are time independent and the system is not moving. So the governing principle was that all these forces acting on the system have to be zero. Some of them, some of all those forces have to be zero, or that means if you resolve those to their components, they have to be zero, okay, in general. And some of all the moments acting on this object have to be zero. For the time being, we are dealing only with 2D, so we forget about this. So what does that mean? In static, as I said, we are dealing with objects. Objects are supported externally, kept in place, so they don't move. They're in equilibrium. Think around, around you. You have a picture frame hanging on the wall. You use a nail to keep this in place. You have a structure that is built, a multi-story building. It is kept in place by its foundation. A tree, okay, is resisting the load that is exerted upon it by winds or birds or whatever, its roots, the chair that you're sitting on, okay? Okay, it is supported by these legs. A bridge structure, okay? All these cars are moving along, okay, is supported by these piers or columns. So any structure you consider in the world, man-made or nature-made, it is supported somehow by some kind of mechanism, okay? The objective of studying the rigid body equilibrium or studying the behavior of these forces under the action these systems under the action of these forces in statics, okay, is this: you have forces acting on a system. You want to find what are the objectives is twofold. The objective is this: the first objective is you want to find the forces that external supports, okay, exert on the system. You want to hang a picture on the wall, right? So this nail, okay, is your support. You hang this picture on the wall, okay? So you do want to know what force this nail will be subjected to. You're designing a light pole, okay? If you want to design the foundation to hold this light pole in place, you want to know how much force this foundation is subjected to. So that is the first objective in statics, that we want to know how much force these external support mechanisms represent. The second objective is we go one step further. We want to find the internal forces that keep pieces of a structure together. The structure is in equilibrium, it's not moving. When you sit on that chair, the chair is not moving, right? So if you want to design that chair, you need to know these different pieces, the leg to the platform that you sit on or the back, they're all connected to each other through bolts or welding or rivets or whatever. You want to know what kind of bolts, what size bolts, what type of rivets, or what kind of welding you should use to connect these. That means what are the forces that develop internally at those joints that you're going to keep in place. So this is the second objective. Okay. So we will start with this first one. That is, we want to find out, okay, how to find the external unknown forces that the structures are subjected to. I'm sure you're going to ask this question, which is a very valid and legitimate question, is, wait a minute, you have all these different types of structures in the world: a tree, a chair, an airplane, a car, a stapler, whatever, that these are all of different shapes and different kinds of supports that they're holding these objects in place. How in the world do you want to tell me that you can find the forces in all these mechanisms of these different shapes and forms that hold these structures in place? My answer is as follows. If you look at the function that those supports play, of course, for the time being, let's focus only on two-dimensional structures. You see that these kind of supports perform no more than three functions. Let me start with this. For instance, you have a light pole or a building, okay? Either the support is such that does not allow any motion in any direction. You have two direction for the forces and one direction for the moment. So no motion in this direction or in this direction takes place, okay? And does not allow even rotation take place. We call this a fixed end support. What that means is that this support is built, designed to resist the structure move in this direction, does not allow the structure to move in this direction, and does not allow the structure to move in this direction. That means this support represents two unknown forces and one unknown moment that are resisting motion in those three directions. This is one type of support. The second type of support is, for instance, a door, okay? These hinges, your beautiful car, okay? The hood, okay, that you lift, okay? Represents, obviously has a weight and load and so on, right? So motion is allowed in this direction, that is rotation is allowed. There is nothing to prevent that rotation in contrast to this one. However, you cannot move this in this direction or in this direction, a door. You cannot move it in this direction or in this direction, right? But you can rotate the door in this direction. This type of support, which we represent by this symbol, we call that a pin or a hinge. So this symbol represents this support, which does not allow motion in this direction, does not allow motion in this direction, but it does allow rotation. So this support can only prevent two motions, translational motions in X or Y direction, but no rotation. Let me show you an example. My stapler, if you look at it in two dimension, this is what is holding this piece in place. So this is the support of this piece, right? So I can rotate it like this, right? But I cannot move it in that direction or pull it in this direction. So this support is preventing motion in that direction or in this direction, but allows motion rotationally. So we call that a pin. There are sometimes cases that you have a support like your chair, especially if you have some rollers here, okay? You're sitting on, okay? You can lift your chair. There's nothing, no force that is, resisting it. You can rotate this, right? But if you want to push it into the floor, you can't. That means this support, sometimes you have situations that you have a slot, okay? And you have a bar, okay, that can move back and forth, can rotate in that slot. We call this support a roller, and we represent it this way. That means this support allows rotation, allows motion in this direction. The only direction that motion cannot take place is in this direction. So this support represents three unknowns. This one represents two unknowns. This represents one unknown. There is a very good table on the second page or the back of your book, okay, that actually tabulates all these types of supports that you encounter in two dimension. This is a roller. I'm sorry, this is a hinge. No, this is a roller. I'm sorry. This is another type of roller, a slot that this can move back and forth. This is another one. This is just a rod, like a leg of your chair sitting on the floor. You can move the object this way. You cannot move it that way, and you can rotate it. So it only represents one unknown force. A cable that is attached to an object. Okay, a cable represents only one force in the direction that that cable is applied. This is a slot that this object can move back and forth, can rotate. So represent one unknown force that is perpendicular to the potential direction of motion. We'll get to that. But this pin or hinge, or if you have a rod sitting on a rough surface which has friction, doesn't resist motion in this direction, represents two unknown forces. And of course, a fixed support represents three unknowns. Okay. So with that knowledge, okay, now we are going to introduce the concept of rigid body equilibrium and solve all the problems. And again, I emphasize for the time being, two-dimensional problems where we want to find out all the unknown external forces that hold the structure in place. For instance, let's say you have a structure made of these two pieces riveted together at this point, another piece which looks like this. This is sitting on an inclined surface on a roller. There's a pin support here. There's a roller support here. Okay. And this is structure may be subjected to unknown uh, forces and moment that are acting on that. So this structure is designed to hold or withstand the action of these loads. The objective, the first objective of rigid body equilibrium is that we want to find out what forces these supports represent, forces or moments these supports represent, with the knowledge that we have now, that this is representing one unknown force, this represents two unknown forces, and this represents three unknown quantities, two forces and a moment. So with that said, let me, start by solving problems to demonstrate the application or how you actually perform this and find those unknowns. Any questions? Okay, so I will start with this example. Let's say you have a beam, okay? This beam is supported at this end, at point A, by a pin that is holding it in place. And then in order to prevent, obviously, the rotation, we have attached a cable here. This cable goes around this pulley that is attached to something. So these two cables that are attached to these points B and C also hold this structure in place. And this structure is designed to hold an 80-pound load. So it's like a crane or something. okay? And the slope here is given 2, 1, square root 5. So is the problem statement clear? And these obviously dimensions are given. This is 5 feet, 5 feet, 3 feet. So the problem is this. The first objective, remember, for the time being, we're going to only focus on the first type of rigid body equilibrium problem. Find unknown forces at external supports. Okay? That is, we want to know what are the forces acting here through this mechanism and through these cables if the structure is subjected to an external load. This is the process or the procedure that I would recommend, and I want you to remember this. This is the only way you can avoid making mistakes in solving these problems. Not only that, it is important because studying statics, the objective is we want to find out if a force is applied to a structure or a structure is designed to withstand certain type of loads, how you want to eventually design that structure. So the algebra, the equations of equilibrium are only the tools. The more important part is to understand how you do the analysis. In other words, you identify the forces and the moments that you're going to deal with to apply equations of equilibrium, right? That's the knowledge we've now gained. What is equilibrium? What is a force? How you represent the force through a vector equation? What is the definition of moment and so on? That is the knowledge. Those are the tools we have learned. Now we are going to apply those knowledge into solving these types of problems. So these are the steps that you must follow in order to not basically get confused. Step one is the easiest step. We've learned in statics that we're dealing with Cartesian coordinate system. And for the time being, we're only focusing, of course, on 2D problems. So you set up an X and Y coordinate. That's the easiest step. Step two is really the heart of statics. I would say that that is 75 or 80% of solving static problems. And what is that? This is the step. This is what this step is. You look at the object that you have, okay? You cut that object from everything that is supporting the structure and the load that is acting on that. That is, you're freeing the object, okay? Then, after you freed the object, you cut these supports, you put back those forces or moments that those supports or external loads represent. External loads are given is easy, okay? So what are the forces that this unknown, this support represent? So this is a pin. So it represents two unknown forces that you have, set up in these directions, X and Y. We do not know. These unknowns are actually acting, these forces are acting in this way in order to keep the structure, but we always just make an assumption. We'll see that if these assumptions, once we solve the problem, the assumption is wrong, you end up with a negative value for these forces. So, but I don't care what direction you assume. Put anything you want, solve the problem, see if the assumed direction is wrong. How about these cables? We know from physics, if you have a pulley, forces on two sides of the pulley are the same. So at point B, if you have this force T, which this cable is exerting on this beam, at this point C, you have also the same force. Okay. This is called, you see, we freed the object from its support, then put back the effect of all these external forces. For that reason, we call this the free body diagram. Okay. Any questions? Step 3 is the easiest step. Step 3 now is you now apply your knowledge of statics, which is knowing that this object subjected to these forces is in equilibrium. Your knowledge tells you sum of all forces along X, sum of all forces along Y, and sum of the moments that all of these forces generate about any point has to be 0. We call these equations of equilibrium, and in the case of dealing with 2D objects, we have 3 of them. That means we cannot have more than 3 unknowns. What do I mean by that? If you had this object like this, fixed support here, then you had these 2 cables going around this, right? You drew the free body diagram of this object. You have this, 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 and these. So you have 4 unknowns. You cannot solve this problem. When you have more than 3 unknowns, we call that problem statically indeterminate. That means your knowledge of statics cannot be used to solve that problem. It doesn't mean that that problem cannot be solved. Your knowledge, which is limited to static equilibrium, cannot be used to solve that problem. Okay? So, with these tools, where do we start? I always recommend, always, no exception, you start with this equation. Why? Because what this means is sum of the moments about any point you consider has to be 0, right? So why not start with summation of moments about a point that is the point of intersection of 2 unknowns. If I use the summation of moments by considering the point of intersection of 2 unknowns at that point, then as you see, I will end up with an equation that has only 1 unknown. So that's why I always recommend to start as the first equation with the summation of moments about the point of intersection of 2 unknowns. So remember that. And second, remember Mr. Saint Verignon is always with you, is watching you. So whenever you have forces, inclined forces, remember to resolve them into their Cartesian coordinates. So here we have then 2 over square root 5 of t. This is 1 over square root 5t. Okay? Now that I have that, I would apply this equation. What do I have here? I have this force going positive moment. This generates a positive moment. This one a negative moment. Okay? I will start with this one. I have negative 80 times this distance, which is 13 feet. This one generates a positive moment, 2 over square root 5 of t times this distance, which is 10. And this one generates also a positive moment. This distance is 5, equal to 0. If you solve this one equation, one unknown, you see that t comes out to be 74.6 pounds. The value for t turned out to be positive, which means the assumed direction that you had for t is correct. And this is the magnitude of that force. Any question?
Do you mind explaining how you got that equation one more time?
Absolutely. I'm glad you asked that question. I would emphasize you start with summation of moments about a point where that point is the point of intersection. See, you have three unknowns. In 2D problem, you have no more than three unknowns, okay, that you need to solve for. If you look at those three unknowns and find there is a point that two of these points intersect, and you take summation of moment about that point, those two unknowns will not generate any moment about that point, right? Why? Because if you have a force, the force, you consider a point along the direction of that force. What is the moment that this force generates about that point? The vertical distance from this point to this line is what? Zero. There is no distance. So a force, uh, does not generate moment about a point that is along its direction. For that reason, these two forces do not generate a moment about point because both of them are going through that point. And this force doesn't either because this force is also going through point A. So moment of this point about point A is also zero. So the only forces that generate moment about point O are those that do not intersect with point O. And these are these forces. Does that explain?
Perfect. Thank you.
Great, thank you. Now that you have one of these unknowns, rest follows. Just write summation of forces along X. You have AX minus 1 over square root 5 times tension, 74.6. Those are the only two forces equal to 0. So you get AX comes out to be 33.4 pounds. Came out to be positive. That means the assumed direction for AX is positive. You write summation of forces along Y equal to 0. You have AY in that direction, positive direction, plus T 74.6 in that direction, plus 2 over square root 5, 74.6, minus this, because it's acting in the negative direction of y, minus 80 is equal to 0. If you solve for this now, you see AY comes out to be negative 33 pounds. So that tells you the assumed direction for AY was wrong. As soon as you encounter this situation, you do the following. You go here, change that direction, put the correct direction here. So this will change and this becomes positive. That means this unknown force acts in this direction. Okay. Any questions? If not, I'm going to do more problem. All right. So let's see. Okay. All right. So let's do one more problem or maybe two more problems, hopefully two more. Okay. So another example. Let's say you have a frame like this, wooden frame, okay, that this is 8 feet long, this is 12 feet tall. It is designed to hold a weight of 500 pounds. To support this externally, you put a uh, pin here, just put a nail, which is a pin, and you put a roller. The reason you put a roller here, because through thermal expansion, you may, have a problem If this wants to expand, at least it can go up and down here. So you have a roller support here, a pin support here. Again, the problem is asking you find reaction or the support forces at, let me label this A, B, C, at A and B. Okay. Any questions? All right. Remember the three steps. Step one, X, Y coordinates. Step two, which is the heart of statics. Okay. The heart of statics, free body diagram. What is it? You cut this structure only from its external support. You do not touch anything inside. The reason I'm emphasizing it, believe it or not, in fact, I had this discussion with some younger colleagues who were, not, had just, not taught the statics for a while. And we had this problem, okay? You have a problem like this was given, okay? So you have, in fact, almost similar to this. So you had a structure that had a pulley here holding a weight, and this pulley is attached to here. And the problem was asking, and this weight is given 100 pounds. The problem was asking, find the unknown forces here. And he drew the free body diagram like this. Okay, you have a pulley here, so it's a pulley. I have these forces. This is wrong. When you're dealing with finding the external forces, you do not touch anything inside the structure. You think of it as just one piece. We'll get to internal forces later on. So this is wrong. Okay? So getting back to this, if I draw the free body diagram, this is going to be the free body diagram. At least that's what I assume as far as the direction. At point B, I do assume that you have a force like this. At point A is a pin, so that represent two unknown forces. And then here you have the applied load. So this is the free body diagram, which, as I said, is 75% to 80% of understanding statics. Okay. Third step is the easiest one. You can call that the brain. If this is the heart, this is the brain. That is applying the equations of equilibrium to solve for those unknowns. And in doing so, as I said, I will always, in 2D problems, always start with this, because I can guarantee you that it always leads to one equation, one unknown, this one. As long as I choose the point about which I want to take the moment, the point of intersection of two unknowns. So why don't I consider point A being that point? Can you think of another point that two unknowns intersect in this problem? Exactly, point B, because you think of it, this force and this force intersect. So I can also take summation of moment point B. Let's do A for the time being. You can try B and you get the same result, okay? So with that, let's do this. So I take summation of moments about A equal to 0. Always consider this as a positive direction. So I have 500 times the vertical distance between here and here, that is this distance, given 8 feet, and this is clockwise, so I have negative 500 times 8. Then this force also generates a clockwise moment. So negative RB times 12 equal to 0. And RB comes out to be negative 3,330 pounds. As soon as I see this negative, I say, wait a minute, I have made a wrong assumption for this force. This means, this negative sign means the assumed direction should have been this way, which is the correct direction. So I fix that. So this gets fixed, this gets fixed. So the direction that this force is acting is this way. Any questions? Now I go to the next step. Summation of forces along x is equal to 0. Okay, so I have AX minus 3,300 pound equal to 0. So AX would be 3,330 pounds acting in this direction. Okay, and obviously summation of forces along y equal to 0. I have AY, the positive direction of y, minus 500, and that's it, equal to 0. So AY is 500-pound force acting in this direction. Okay. Any questions?
I have a question. Is the
Sure.
reason like support plank isn't anything to do with this because like as long as it doesn't break, it'll just like kind of cancel out
Which one?
the like diagonal plank in the middle?
Oh, no, at this point, we are only interested in finding these external forces. There are something going on inside, obviously. This is definitely there for a purpose, for a function. And that function is to put these, to hold these, but I don't care at this point. At this point, all I want to find these external supports. So I just close my eyes. What is happening inside the structure? I assume that I'm just dealing with a single piece that is supported at these 2 points externally, because all I want is to find external reaction forces that are holding the entire structure in place. I don't care what is going on inside. Later, we'll do that. We'll find out what is the force here, what is the force here. But this
Okay,
is very important.
thanks.
I'm glad you asked that question. Very good and very important question. Okay. So the good thing is, in your section, we ended up with more time, which is good. That means I can do one more problem. Let's see, I'm gonna do another interesting problem here. There we go. Let's see. Okay, here we go. I'm gonna do this problem. Oh, you know what? I was hoping to do a pulley problem. I love pulleys. I'll do more pulleys later. Okay. Oh, here we go. Here we go. No. Okay, let me do this problem. You have a beam or a frame of some sort that looks like this. It is pinned here at point B. This angle is given 60 degrees, and a load perpendicular to this leg is applied 6 kilonewton at a distance of 0.8 meters here and 0.4 meters here. And then you have another load acting here in the middle of this piece, which is supported at this end by a roller, 10 kilonewton, and these distances are given. Okay, this is 0.6 meter and 0.6 meter. Okay, so this is A and B. So the problem is asking you to find forces at A and B at support reactions. Okay. In the interest of time, I would be a little bit lazy instead of, maybe not. It's not a good idea. I'll redraw that anyway. So step one, X, Y coordinate. Step two, take that structure, detach it from its external supports, put back all these applied loads, okay, 6 kilonewton, and then the action that these two represent, you have a roller, that means you have a force only in this direction. Remember, when you have a roller, the unknown force is perpendicular to the potential direction of motion. This is going to move in this direction. So the unknown force is always perpendicular to that. Here, you have two unknown forces. I consider them to be acting in these directions. Okay. And this is 60 degrees. This was 0.8 meter. This is 0.4 meter. This is 0.6 meter and 0.6 meter. So this is the free body diagram. Third step, which is the easier step, start with summation of moment being zero about the point of intersection of two unknowns. Again, here, if you think of it, you can consider this to be that point. Doesn't have to be that, right? Instead, for the heck of it, why not? Why not looking at that as, but it's going to take more time, so I'm going to do this one. You try it at point C here. You should get the same results, but I'll do it at point B, okay? And always this is considered the positive direction. So no moment for these two at point B. So you have only this force that generates the moment. This is the vertical distance from here to point B, and it's moving in this direction. So that'll be positive. So we have 6 kilonewton times the distance given, zero point 0.4. Then what else you have? Moment of this force. And that is something you have to find because you have 60, you are not given this direction, but you've been given that. This is 1.2. So this is 1.2 cosine of 60, which is the sine of 30. So that is 0.6. So the vertical distance from here between this and this moves in that direction would be what? So you have 10 times 0.6 also because it generates that moment. How about this guy? Is rotating about point B in that direction. So that would be negative RB times this distance, which is 0.6, 0.6, 0.6, 1.8 equal to 0. That will give you RB that comes out to be 5 kilonewton acting, I'm sorry, RA, okay, RA, that is acting like this, okay? Any questions? How about for these now? Simply write summation of forces along x equal to 0. If you do that, you have only bx. This one and this one don't generate any force component along X and Y, you only have these two, right? And if you resolve, this is going to be, if this is 60, this would be 30 degrees, this would be 60 degrees. So this one, you have negative 6 times cosine of 30 degrees, and that's the only force you have along X equal to 0. That'll give you Bx. That comes out to be 5.2 kilonewton. Came out to be positive. That means the assumed direction is right, and it is acting in this direction. Then you have sum of forces along y equal to 0. So you have By minus this component, which is 6 sine of 30 minus 10 kilonewton plus Ra equal to 0. And that will give you By comes out to be, also happens to come out to be 5 kilonewton in this direction. Okay. Any questions? No? All right. Sorry, I just noticed that you have a question in the chat. So slots and roller in terms of statics are exactly, they are the same. Slots and rollers are the same. Yes. Okay.